So here's a Raoult's law problem, and Raoult's law is also known as the vapor pressure lowering law. So let's write that down. Vapor pressure lowering law. It basically says if you mix two things, you'll lower the vapor pressure of one of them. So if you have something with a high or a relatively higher vapor pressure, you mix it something with a lower vapor pressure, you're going to get a lower vapor pressure for this thing. So the vapor pressure of 2 is going to be lower than 1 after it's mixed with this star over here. So let's read the question. It says, which of the bottom temperatures is the boiling point at 1 atm of a solution containing 116 grams of acetone? Let's ignore the molecular weight. And 72 grams of water. So the equation we know for this is going to be P total pressure of the mixture. It's going to be equal to the partial pressures. So it's going to be equal partial pressure of water, PW, plus the partial pressure of acetone. And we can go ahead and show how we solve for the partial pressure of acetone. We basically take the mole fraction of acetone, which is the amount of acetone present in the whole thing. We multiply it by the original pressure of acetone. And let me switch these because I want to do something in a minute and I'll make it better that way. So the original pressure of acetone times the mole fraction of acetone, and then plus the original pressure of water times the amount of water in there. That's why it's called colligative properties, because as you can see, if the mole fraction of either increases, the amount of the pure pressure which you can get is going to increase. So we just take a proportional amount of our pure pressure. So if our pure pressure is 4, 1 4, well, that's going to give us 0.25, but or I'm sorry, that's going to give us 1. So 4 divided by 4 is 1. So if our original pressure is 4 and this is our mole fraction, it only gives us 1. But if it's 4 and then we have like 1/2, for instance, we have 4 over 2, which is 2. So you can see how the amount that you have in it is going to let you take more of your proportion of your pure pressure. So how do we solve this if it's asking for boiling point? Because this equation solves for total pressure. Well, you have to remember that most things, when we do most problems, we're talking about standard conditions. So standard pressure is 1 atm, standard atmospheric pressure. And the thing about boiling is it doesn't happen until the vapor pressure of any liquid or a mixture of liquids is equal to the outside pressure. So this would be the vapor pressure. Once it's been heated up, we heat it up until it reaches 1 atm, which is equal to the pressure outside. But if you're in an environment that's like 1.05 atm, so you're in a higher pressure environment, maybe you're lower, like in a valley somewhere, then you're actually going to need your vapor pressure to be 1.05 atm to boil your liquid, because basically they have to equal each other so that the molecules in the liquid phase can break through and join the gas phase here. Okay, liquid gas. So let's look at the chart now. And well, let's talk about what this means first. Or let's look at the chart and talk about what this means. So as you can see, for water here, if we look at 100 degrees Celsius, we have 1 atm, and that's why water boils at 100 degrees Celsius, because it's finally reached 1 atm. Here at 90 degrees Celsius, it's 0.694, so it's not boiled here. Similarly, you can look at acetone, which has a boiling point of 56 degrees Celsius. At 1 atm, this guy is going to be boiling. So actually, it requires way less heat for acetone to boil than water. So it requires about like whatever 100 minus 56. That's the difference between energy that water will require. That's because water has hydrogen bonds and acetone doesn't. And this is the structure of acetone. If you draw the molecular structure, C3H6O, there's no hydrogen bonds. There's a dipole here, but it's not as strong as a hydrogen bond, which is present in water, which makes dipoles towards the electronegative oxygen. So that's why it takes much more heat to boil water. So obviously, when we mix these, water is the one with the higher vapor pressure, right? So when it's mixed with I'm sorry, not higher vapor pressure. It has, let me reword that. So what we want to do is lower the vapor pressure water boils at. So water boils at 1 atm normally, but because it's mixed with something, the vapor pressure, which it's going to boil at, is going to be lowered, right? Because it's mixed with something that already is kind of at higher that already boils at higher already boils like way over here. So what's actually happening is it's gonna boil at a lower vapor pressure for water and a higher vapor pressure for acetone, because it has to be somewhere between the 56 and the 100, right? When they mix, their boiling points are also going to mix. Water's boiling point is going to lower, and acetone's vapor boiling point is going to go up because it's mixed with the water. So let's go ahead and see how we're going to solve for that. So we're going to do that by putting this whole equation that I've written down here equal to 1, because it still takes 1 atm for something to boil. It has to equal atmospheric pressure, but what's going to happen is someone's going to have a little bit of a higher vapor pressure, and someone's going to have a little bit of a lower vapor pressure, and you'll see that in a second. So the mole fraction for water, I'm going to let y'all do the math because it takes a little bit of time to do that, but I'll describe it. It's basically going to be 2/6. And the mole fraction, oops, I'm sorry, it's going to be 4/6. And the mole fraction for acetone, it's going to be 2/6. So all I did was I found the moles of water, and then I found the moles of acetone. And here's the moles water, it's 4. Here's the moles of acetone, and I put them over 4 plus 2, which is 6, the moles total. So now let's look at the pure pressure of acetone and the pure pressure of water. So we're not going to be using any pure pressure of acetone and any pure pressure of water. We have to use the one which is at the temp which water boils. Why? Because water boils at 1 atm. And that's what the question's asking for, right? The temperature which water boils, and it boils at 1 atm. So we look at our list and we have 70 degrees, 80 degrees, 90 degrees. So we have to see which one of these vapor pressures, when this goes here for acetone and this goes here for water, will it equal 1? Or how about 80 when you put it there and you put this there? Will that equal 1? So it's just trial and error. So let's go back to block. So let's try and I've tried these already. I can tell you that it's not 60 degrees, it's not 70 degrees. The answer is 80 degrees. So when you plug in 2.12 atm, so that's the vapor pressure acetone will be at 80 degrees, and 0.456, that's the vapor pressure water will be at 80 degrees, that you can get the mixture to boil at 1 atm. So, and that's pretty cool, right? Basically, this usually would be a gas, acetone would be a gas, but because it's mixed with water, and then what we do is we take a part of it based on our mole fraction, we can get 1 atm, which is our boiling temperature, 80 degrees Celsius, which is the 1 atm, which 80 degrees Celsius is when it'll boil at 1 atm now. Well, that's Raoult's law. I'm not sure if I'm missing anything. And we didn't have to try out 56 degrees Celsius, and we didn't have to try out 100 degrees Celsius. So we didn't, because that's 1 atm and 1 atm. And these are the original pure, like this is at 100 degrees Celsius, this is at 56 degrees Celsius. We know it's not going to be these because these were when they were at their boiling points at 1 atm respectively. So it can't be either of these because this is going to be two different temperatures, right? We don't have to we know it's not going to be just 56 because that doesn't account for water at all. It's not going to be just 100 because that doesn't count for acetone at all. It has to be somewhere between, because when they mix, they give something in between. And that's why it's called the vapor pressure lowering law. Because as you can see, water's vapor pressure was lowered by adding acetone in it. And of course, acetones was made higher, but we are just looking at it from one perspective. Let's do a more standard question. Let's go up here. This is a little bit more straightforward. It just says calculate the vapor pressure of a mixture with 252 grams of pentane and 1400 grams of heptane at 20 degrees Celsius. So cool, we know it's at a constant temperature. So we know that constant temperature is going to have a respective vapor pressure assigned to it for each. And what do you know? Here it says 420 mmHg for heptane. So at 20 degrees Celsius, this is where this guy is, and 36 mmHg at 20 degrees Celsius, this is where heptane is. So let's go ahead and write our equation. P pentane plus P heptane is going to equal P total, our pressure total. So the partial pressure of pentane is going to be the pure pressure times the mole fraction of pentane. So the pure pressure apparently is 420 at 20 degrees. And the mole fraction, I'm just going to go ahead and put in right now. It's going to be 3.5 over 3.5 plus 14. So moles total are on the bottom for pentane plus heptane, and moles of just pentane on the top. Plus the mole fraction of heptane times its pure pressure at 20 degrees Celsius. So this is going to be 36, and this is going to be, well, 3.5 plus 14 is total moles. And then the moles of just the heptane are 14. So now you can solve, and the answer is 1.0.8 mmHg. So as you can see, pentane, its vapor pressure, which it boils at in 20 degrees Celsius, got lowered to 112 degrees 0.8. So Raoult's law is indeed present here. And if this, it didn't talk about what the atmospheric pressure outside is, but 1 atm standard is also equal to 760 mmHg. So this would not boil. The mixture would be a liquid, because it would have to raise much more. So one way we can make it raise would be perhaps to increase the mole fraction here, so we get a larger, basically get a larger percentage of the pure pressure of pentane, since it's a little bit higher. But the thing is that it still wouldn't work because there's not enough heat, because 420, that's as high as we can go, right? Because that mole fraction would just have to be 1. And then that would mean this mole fraction 0. That means it's just pentane by itself, and it still wouldn't boil because it would have to reach 760 mmHg. So that means at 20 degrees Celsius, even the pure version of pentane and heptane is a liquid. So that's that. Thank you for watching this video, and have a great day.